So we can go from these small oscillations or even you use an LED. There you have it. We could convert these oscillations into a tone so that when you connect a speaker like this, get a tone like this with the speaker in place of the LED. We can even change the frequency of oscillation like this by just replacing the capacitor here. And we have something new going, right? We could even get a higher tone, higher frequency by adopting a smaller capacitor like this. Like this. See what I'm talking about? And all this is about positive feedback. Let's get into it. Okay, so today we are going to learn how to build a simple burglar alarm tone, which we shall later rely on to construct a complete alarm circuit. So you can notice I'm taking everything apart from the board. Everything is just being taken apart. So in this experiment, what shall we need? We shall need two transistors, TRP42, TRP41. We have used these transistors in our earlier videos, so I want to believe you are familiar with the pinouts. We shall need a 47 kilo ohm resistor. We shall need a 10 microfarad capacitor. We shall need a 22 nanofarad capacitor here. Then we have 1 microfarad capacitor. The voltage rating is not critical to our circuit. That's why I have chosen to ignore them in my introductions. Then what else shall we need? It's all we need. Let's get started. But before then, let's see how the circuit works. So today we are learning about positive feedback. Positive feedback occurs when you have a circuit like this. You have an NPN transistor, bias with RB at the base, which goes to the positive terminal, right? And then we have the collector of this transistor, which is fed to the base of the succeeding transistor, which is a PNP transistor, which also goes to the positive terminal this way. The collector goes to ground by a small resistor. It's a load resistor. Let's call it R for load resistor. And then we have the emitter of transistor T1, this is with T2, which also goes to ground. Both go to ground, the negative terminal. Okay. But this is a secret. We are feeding the collector of T2 to the base of T1 so that it reinforces the input of T1 so that it turns on even harder. This is our resistor on base. It is 47 kilo ohm. Our load resistor will range from 1 ohm to 10 ohm. I'll tell you why the load resistor is so low. Our feedback capacitor, we're going to be changing it as the lesson assumes progress. So we're not going to attach a value to it. But basically, this is how the circuit works. Initially, if you study the circuit closely, you notice that whether transistor T2, which is the PNP transistor, will turn on or not depends heavily on the support that transistor T1 provides. Because the collector of T1 is attached to the base of T2, T2 will only turn on if T1 is on. Okay, so T1 turns on initially by the voltage divider network formed by RB, our 47 kilo ohm resistor, with the feedback capacitor. The first capacitor we shall use is 10 microfarad. This is how it turns on. As you power on the circuit, the feedback capacitor begins to accumulate voltage. As soon as it reaches a value of around 0.7, T1 turns on. As it turns on, you notice that the base emitter junction of T1 is also parallel to this capacitor. So the capacitor is neither able to charge further nor discharge because the base emitter junction of T1 is parallel to it. Now, T1 is on. It also turns T2 on, whose emitter goes to the positive terminal directly. As T2 is turned on, a voltage develops on its collector resistor here, which actually causes the feedback capacitor to charge even higher, depending on the voltage which RL accumulates. Remember, when you put a capacitor in series with a resistor, the capacitor will charge the value of the initial voltage on the resistor. So this capacitor charges based on the voltage that is collected on RL here. As the voltage builds up, now look at this loop here, from here up to here. T1 is now powered by this loop. The voltage developed from this loop from here up to here. But as the capacitor is building up, it is also losing current. The loop you see here is also losing current. So as the capacitor builds up, this transistor will have to turn off. T1 will have to turn off because initially its base current will be close to 0, which also compels T2 to turn off. As T2 is off, its voltage on the collector load also reduces to 0. Remember, the capacitor voltage, final capacitor voltage will always equal the voltage on the resistive load. So this capacitor has to now discharge to the equivalent voltage on the resistive load on T2. So if it is 1 ohm here, it is multiplied by beta, which is the total resistor which the base emitter sees, which also discharges the feedback capacitor. As the feedback capacitor is discharged, the cycle repeats. It is charged again by RB and the feedback capacitor. Enough voltage is collected on this, which stops current from flowing through this loop. And then, as the T1 goes off, T2 also goes off, the voltage on RL here becomes 0, so that the capacitor will now have to be forced to equate its voltage to RL, which situation is created by the discharge of the feedback capacitor by this network. And it goes on and on. We have said already that the only way that we can vary the discharge and charging time of the capacitor is to vary the feedback capacitor, because it is the only element which is common to both the discharge part and then the charging part. Let's see if we can build a circuit step by step now. So the first transistor we use is a TIP41C transistor. It's an NPN transistor. Let's insert it. Look at the way I've turned it. This will be the base by virtue of its position and how it has been turned. And this will be the collector. And the last will constitute the emitter lead. Let's insert into the breadboard. Good. Now, we have a 47 kilo ohm resistor which we shall connect to the base of the NPN transistor and then connect it to the positive rail. By practice, I always connect my negative rail to the exterior line here and then my positive rail to the exterior contacts here. So I'm going to drop a jumper wire, and then the jumper wire is pretty short. Let's get a longer one. So from the positive line here. Good. So now that is done. And we are saying that according to our circuit, the emitter of this one goes to ground, right? Okay. So let's put it here. This is the ground terminal, which is negative, this circumstance. And then the negative I've put here, negative, I'm connecting a jumper from here, from the emitter to the negative rail. Which when fully assembled will be inserted here. Okay. Now let's get to our PNP transistor. Again, the pin connections are the same, but notice that this time it is facing the it is facing the NPN transistor face to face. So this time the emitter rather comes here, the collector maintains its position, but the base is now downwards. So here. So for the NPN transistor, this is the base, this is the collector, and this is the emitter. Good. Now we are saying the collector of the PNP transistor, according to the circuit diagram, feeds to the base of the PNP transistor. So the NPN's collector here feeds to the base of the PNP transistor. This is what we have so far. Right? Make this clear for you. Okay. Oh, good. Let's continue. Now we are connecting this load, which is an incandescent bulb, draws about 300 milliamperes of power. Since this is a PNP transistor, we attach it to the collector, which is the middle lead, and then it comes to the negative ground. So we'll tap the negative terminal from here to here. So that is our RL, which we saw in the circuit. That one is done. Now our feedback capacitor is taken from the collector of the PNP transistor, which is the second one, to the base of the NPN transistor. This manner. So where is the base? I could pick the base from here. Just keep an eye. So I could get it here. The base is here. Okay. So that is done. And according to the circuit diagram, the emitter of transistor T2, which is the TRP42C, goes to the positive rail. So this is emitter. I insert it here, right? And it goes to the positive rail. I can tap it here. I think I missed the positive rail for this one. Good. So there you have it, right? Good. So what's left? I think we are ready to test the circuit. So let's test it and see. Before we power it up, I want to make sure these lines are continuous. So I'll put a jumper here to link. Notice that there's a break here. Then I'll make this one also continuous. So now let's power it up and see. Let's replace this small 1 microfarad capacitor with the 10 microfarad capacitor. So collector to the base of this one. And this is the negative terminal to the battery. I'll insert it here. Like I said, I'll do this by custom. And then I have the positive terminal here, which I shall insert here. There we go, the oscillation. See, the circuit is oscillating, right? If we want it to oscillate faster, we just have to change the capacitor, which we shall do right now. So that's the oscillation going. If you don't have this incandescent bulb, you could use an LED. But there's one condition. We will need to connect the LEDs in parallel so that its total internal resistance will be very, very low. Because whatever resistance we present in the discharge part will be multiplied by the beta of the NPN transistor. That's why we need this LED to have a very low resistance. So we connect them in parallel and then we have a low resistance. So let's put the LED in the stead of the incandescent lamp and see what becomes the circuit. So let's connect the LED like this. It will come in place of the collector. Yeah. Go to the, you notice that the oscillation is not happening. Let's increase the voltage and see. Let me increase the voltage supply. So now, right now, I'm operating on 6 volts now. Run the circuit on 6 volts now. Now let's see if we can generate a tone. So we are coming to replace the LED with a speaker. This is a speaker I salvaged from my music box. Let's put it in place of the LED and see what happens. Let's remove the LED. First, let's take the power off. Then get the LED out. So these are the terminals to the speakers, right? Let's insert them in place of the LED. This is the collector one. And this is the negative rail. Let's insert the positive lead or the power supply and see if the speaker will start popping. You can actually hear the speaker popping at the frequency at which the LEDs were oscillating. See that? Okay. Now let's see if we can increase the frequency a bit. Let's take the power off. I'm putting a 1 microfarad capacitor there. So here. So this one will go to the collector of this one. And let's see what happens. There you have it. Okay. Let's put this capacitor there. So the value, I surveyed it from a circuit board. I want to believe it's 22 nanofarad, but the value seems rated in Chinese, this one. But it is far, far smaller. If you get a 22 nanofarad, put it there and see. Let's replace this one with it and see what becomes of the circuit. So it goes here. Then to the collector of this one. Let's power it up and see what becomes of the circuit. So there we go. Initially, the frequency sounded a bit high because the impedance of the speaker is a bit too low. If you have a bigger speaker, you get much better results. So this is the basis of our burglar alarm circuit. In electronics, we build things step by step or stages by stages, and then we put them together and have a whole unit working. So it's important that you appreciate what you have done today. Next time we'll take another session of the burglar alarm circuit. We'll design it. When we finish, we'll put everything together and it will all behave as a single coherent unit. Let's have a closer look at our assembly. Right? Okay. So don't let anything confuse you here. All right? Okay. Let's look at the other side. So it's really very simple. If you're not sure of anything, hit me up in the comment section. All right. Take care.